All right, I guess we can slowly get started. Hi everyone, thanks for joining in this session. So this session is the third session today in the virtual MATLAB Day series. Um, so in this session, we will give an overview of deep learning in MATLAB and how it can be used for applications in engineering and science. My name is Bo. I'm an application engineer based in our Bay Area office. We also have a team of math workers here joining us in the panelists. So they're Ijon, Esperanza, Courtney, Ryan, Sharon, and Sumit. So if you have any questions or if you have any comments, please direct them into Q&A or chat. So please make sure that you direct all your questions to Q&A and other comments into chat. And please direct your questions to panelists so that everyone from our team of MathWorks will be able to address your questions or comments. And also please participate in the polls and so that I will be able to adjust the presentation slightly based on your responses. So if you have a problem hearing the audio from the WebEx, please also try to join us through phone. So we have a dial-in number here. And once you dial in, you can input the access code to access the audio through your phone. Okay, wonderful. So today we have the full virtual MATLAB day going on. So this one is the deep learning with MATLAB session. Later, after the 30 minutes after the finish of this session, we have a learning MATLAB and career path. I strongly encourage you guys to join as well to receive additional information and resources to better get you started. And without further ado, let's start today's presentation. So there will be three key sections in today's presentation. And this presentation is going to be an hour. We're going to spend about 20 to 30 minutes to an actual demo to show you guys how to build a deep learning workflow. And then we'll stay here after the hour mark and answer some of your questions and comments. So the aim of this session is to provide a clear view of overview of deep learning. What is deep learning and where deep learning can be used and applied in the field of engineering and science. In the second section, we'll address how can we research, develop, and deploy our deep learning algorithms into a productization platform. Last but not the least, what we MathWorks have to offer to better support you, help you achieve your success in the field of deep learning. So for those of you that might have a problem with the audio, we have put the audio connection information in the chat window. The slides will be sent after the session, so you will have access to the slides of this presentation, as well as some other materials as well. All right, without further ado, let's get into the presentation. First, let's briefly talk about deep learning and its use cases in engineering and science. Nowadays, we have seen many popular consumer applications of deep learning. These include speech recognition using the smart speakers, face detection for cameras on the phone, as well as automated driving, self-driving system in automotive vehicles. There are many, many other mainstream applications that we're using every day. But how many of them would you guys consider being applicable to engineering and science? Well, here shows some of the key applications in some key industries that involve deep learning across a wide range of industries and applications. For example, in aerospace and defense, deep learning can be used to analyze satellite images and detect objects of interest. What about automotive? In automotive industry, we can use many techniques, including one called semantic segmentation for automated driving applications by segmenting the drivable path and other objects such as cars, pedestrians, and warning signs. People been also widely adopting deep learning in manufacturing as well. So they use it to automate the process to find defects in the items. And so these kind of inspections were previously done by the engineers on site. And same to many other applications such as medical device, wireless communication, and so on. Here at MathWorks, we are also seeing a growing trend of application being adopted that involves AI-developed solutions. For example, in aerospace and defense, Airbus performs automatic defect detection via deployed models running on embedded GPU. In automotive industry, Denso is modeling, simulating, and deploying models for their complex electronic control units, ECU. And in energy production, Shell has developed models by combining traditional wavelet approach together with signal processing and deep learning for earthquake detection. And of course, deep learning has been used in research as well. So on the left side, we're showing a research where researchers automatically predict cancer from complex medical images and leverage the pre-trained networks available in the MATLAB platform called AlexNet. This research has been published on Nature. On the right side, researchers convert brainwave of ALS patients into words and phrases by combining wavelet approach as well as deep learning for signal processing. I believe this is a research group from UT Austin. As we can see from both the industry and academia, engineers or researchers, they are able to quickly carry out many ideas and save time on the nitty-gritty details. In the industry, they're able to reduce their operational costs, improve the revenue, which established leadership in the industry. And in the research, they're able to quickly try out many ideas, focus on research, and carry out research breakthrough. As we can see, the deep learning is a vital topic for us to gain an understanding into nowadays. So with this being said, what exactly is deep learning? Or broadly speaking, what exactly is artificial intelligence? So generally speaking, artificial intelligence, AI, is the ability to learn from data, gain intuition without explicitly setting the rules, so that we can solve the problems by automatically by ingesting some data, feeding the data into the model. And we just need to allow the models to learn from the examples. And AI is a very broad field that contains many topics. You guys might heard planning, scheduling, expert system, recommender systems, robotics, perception, as well as machine learning. So machine learning is a subset of the artificial intelligence that utilize some statistical methods that enable the machine to learn from tasks so that we do not need to explicitly program and setting the rules. And deep learning is considered a subset of machine learning that utilize a very specific and interesting architecture called neural networks that is inspired by the human biological structure of the brain. Because we all know that the human biological structure of the brain has the most efficient information transfer rate, so that we can extract and brain regions as nodes and correlation or the relation between the different brain regions as edges, so that through this multi-layer of neural networks, we're able to generate features and then make a decision using the specific deep learning network. Although it's inspired by the human brain, it also involves some statistical principles in it, which makes it extremely powerful. And many of you guys might wonder, what is the deep learning? What is the difference between the deep learning versus machine learning? So generally speaking, I would advise that we try both of the technique to make sure that our model performs the best. So it's like I'm having a breathing issue. I think my presentation is freeze. So let me see if we're able to quickly solve this problem.
Hi, Bo. Yeah, we see like two slides put together somehow.
Yeah, so my screen is frozen, and there's
No way to bring it back.
no way to bring me back.
Okay.
So, which is not a good sign.
So if you want, you can try to rejoin, or I can try to make you host and see whether that troubleshoots the problem.
Yeah, can you yeah, make me the host and see if that refresh the software?
Yes, let's try.
Currently, I'm freezed at deep learning versus machine learning slide.
Okay, I made you the host.
Yeah, so I cannot see anything on my screen now.
If you want, you can try to rejoin.
Yeah, so I don't think my computer is responding at all. I might need to restart the computer. If this is the case, then
If Sharon is around, maybe she can take over.
yeah, Sharon, do you have the presentation slide deck? Sorry, I don't want to put you like unprepared, but if you can maybe just start from the introduction, that would be very
Yeah.
helpful.
No
All right,
worries. Let me pull
wonderful.
that up in the meantime.
Yeah, so let
give
me hop
me-
off. Yeah, all right.
Give me a quick second. So bear with us, everyone. I'm just going to grab that slide deck and open it up for you guys. Here it goes. Okay, deep learning for, I believe he was doing the signals example.
Which is fine. I think we can showcase the signals as well as the images, whichever works the better. Yeah.
Okay, so let
Yeah,
me.
whichever you feel the most comfortable with.
I think they're quite similar, so let me just
Okay, wonderful.
grab them. All right, so let me find
Okay,
that slide you
so
were on. All right.
all right, wonderful. Thanks a lot.
No worries, no worries. All right, so let me just share my screen over here. Okay, I believe this is where we were. Okay, everyone can hear me and see the screen? Type yes in the chat if you can.
Yes, I can
Lovely.
see your
Awesome. Thanks.
screen, Sharon.
All right. Okay, so Bo was talking about how, deep learning is a subset of the machine learning capabilities. And I believe he was about to pivot over to kind of how you would think about when to use one or the other. So just to give you a little more of a level set of exactly how deep learning works. So deep learning, like Bo said, is using neural networks, which was initially inspired by the way that we tried to model the way the brain works. So each of these layers have these computational units called perceptrons, essentially. And some people call them neurons. Some biologists are like, don't call that a neuron, right? But basically, each of these units, in the layer, you can assign any arbitrary function to take an input to an output and then pass it on to the next layer. And with your input, this may be signals, it might be image data, and ultimately your output, if you're doing classification, you're going to maybe classify an image as cat or dog, or you may be performing regression and looking for a value that is more continuous. The real magic is happening in the hidden layers, right? The hidden layers of deep learning, when you have two or more layers, it's a deep neural network. That's what's roughly considered as deep neural network, and that's why it's called deep learning. And as Bo was pointing out, deep learning is more of a modern field, more recently used field within machine learning. And this is because this is a very computationally intensive process. You need a lot of data, and you need to be able to compute the weights and biases inside each of these layers and each of these units to learn from our data. So that is what the neural network is doing in deep learning. Okay, so the trade-off is this, right? I alluded to this a little bit already. Deep learning requires a ton of data, usually at least an order of magnitude more than a typical traditional machine learning method. So for traditional machine learning, right, we're typically picking the model and pre-digesting some of the information in the data for that model. So if we're classifying images of vehicles as car, motorcycle, SUV, we may say, okay, concentrate on the number of wheels, concentrate on the shape of the vehicle. And for, your given data set, it might be the mean, it might be in an image, the edges and contrast. So whatever it is, you may need to pre-digest some of that information for your model in traditional machine learning. So the trade-off there is that feature extraction. For deep learning, the feature extraction is done automatically through this neural network structure. The trade-off being you need a lot more data. So these are all things you want to consider when you're trying to decide between machine learning and deep learning. Do I have enough data? Do I have the computational power to be able to train a neural network, or can I train a model that's simpler? And in both of these situations, if you're doing supervised machine learning or a subset of that deep learning, you want to have labeled data. So you need to think about, do I have the bandwidth to label all of my images or all of my signals? All right. So let me walk you through kind of the step-by-step of the deep learning workflow. And Bo, let me know if, if you're still gearing up for getting ready to present again, or if you would like me to, I'm not sure if my slides are exactly the ones that you were going to show today, so feel free to interject if you see anything. So,
Yeah, so we can connect at the section 3, so the MathWorks deep learning support. So there are some specific slides for the campus-wide license and MATLAB Central, but yes, please go ahead for this first and second section. Yeah,
sure. Yeah. So actually, let me make sure that I'm just gonna make sure that I have the slide deck here that addresses both signals and images, and it's kind of more flexible. I think the one I have open right now is very, very heavily on images. So let me just make sure I have that. Well, this part is the same, so let me go through this first. Okay, so the step-by-step, how do we implement deep learning, right? So the first step for really any kind of machine learning workflow, which deep learning is part of, is the preparation of your data, right? You need to have enough data, but because it's not a perfect world, you need to clean up your data. You need to pre-process it for signals and images alike. You may have noise. You may have just things within your data that must be eliminated before you pass it through a model. If you don't clean up your data before you give it to your model, chances are it won't learn the way you need it to learn. So that's a big step, and labeling your data is also an incredibly time-consuming manual task if you don't have a way of automating it. And you bring to the table the ability to label your data as a domain expert of your data. Right. And then there are also situations when we want to be able to use deep learning but don't have enough data. Right? We may have the computational power, but our data set is just not there, or one category of our data is not quite enough. So in cases like that, we can think about how to augment or generate or synthesize more of our data as well. So those are some considerations on the data side. On the modeling side, you do have to think about, do I have the expertise when I'm first entering this deep learning domain? Can I actually build this model, or do I need to turn to the literature and pull models from different frameworks, different open source frameworks that have been published by researchers? Perhaps you want the latest, hottest new model from the research hot off the press. Can I be able to pull that off the framework into the MATLAB environment or whatever environment I'm working in? And how do I tune my hyperparameters? How do I make sure that I'm making all the adjustments necessary for my model to work well? And like I already mentioned, training can take a long time because you have a lot of data and you have potentially very complex networks. So how can I speed up this process using hardware like GPUs, cloud resources, clusters? Anything you can get your hands on in terms of parallel computing is helpful here. Okay, and also, how do I integrate my model? And this is kind of the next step in this step-by-step workflow into a larger system, right? Usually when we're creating a model, maybe we're publishing it, but it needs to fulfill some kind of goal or task, right? So if we're creating a model to identify tumor cells in an image, hopefully someone is going to take that model, put it into a system so it could help a medical professional more automatically and quickly detect cells in a biopsy slide, right? So within a larger system, how can I make sure my model is working well and that whole system is tested and ready, especially for taking it all the way to like a project or product or competition phase? Okay, and then how do I ultimately deploy my model? Perhaps this is to hardware, perhaps I'm scaling up and deploying it on a website or a mobile app. How can I do all of that without the tedious task of rewriting all of my algorithms to fit into that environment or that programming language? So I'm happy to say MATLAB can actually support any and all of this workflow. So for those of you who are already using deep learning, you may be using open source tools that are already firmly embedded in your workflow, and that's okay. A lot of our customers have a hybrid workflow where they might use MATLAB for labeling their data and move some of their steps into open source and come back to generate code for deployment onto hardware. So there are a lot of flexible ways to use this workflow. And if you're new to deep learning, you can use this entire workflow seamlessly within MATLAB as well, and still have access to Python and other open source frameworks for models and co-execution of your code. Okay. So as Bo already pointed out, there is an incredible range of uses across many different industries for deep learning. So again, highly encourage you to check out those user stories available on our website to find the ones that are most relevant to you. Okay. And he's already gone through these slides, so I won't go through those again. I think what I can do today is go through an example with images, but do keep in mind, this workflow can also apply to signals. So in a similar way that we can detect objects in an image, you can also parse out events in a signal or pieces of a signal that would be classified into different classes. So all of the techniques and built-in functionalities I'm talking about today are you can apply them across the board to both images, signals, and also text, 3D volumetric data, LiDAR, 3D point clouds. So we have a really good range of support for all of these different domains and areas. But for the sake of demonstration, let's look at a demonstration of YOLO V2, so a real-time appropriate object detector, which is orders of magnitude faster than previous, albeit more accurate object detectors like RCNN, but this one is able to take one pass of the image rather than thousands and do this much quicker. So Let me see. I think I just saw a very relevant question. So what is RCNN? So RCNN is a type of object detection algorithm, and so is YOLO v2. But RCNN works in a slightly different way, different manner in which it takes several hundreds or thousands of passes through an image to find kind of these regions of interest where an object may exist, and then see if that object exists. So YOLO v2 does one pass and is able to take this image and use a CNN, or a convolutional neural network, which I'll explain in just a second, and go ahead and do feature extraction, so that digestion of the image that I was talking about. So if we're, categorizing pictures of cats and dogs, what parts of the image should we focus on? Should we focus on the whiskers, the shape of the head? What features of the data are important to classifying that image? So in this case, a CNN is a useful tool for that kind of feature extraction in the front end of the YOLO v2 network. In the second part of the YOLO v2 network, we're using a decoding piece. So in each of the regions of interest that were identified in the first piece, is there or is there not an object? So it's important to keep in mind this kind of workflow can easily be connected up to, classifying multiple types of objects as well. So it's very flexible if you, of course, know what you're doing, and if you leverage the power of networks that have already been trained by others. I've got another question. What does YOLO stand for? So it's actually right here. And if you want more information, you can click on this link once you get the slides. It's the You Only Look Once network. It's referring to how you just make one pass of the image to find these objects. All right, so we're going to build one and build a network. Part of it is going to be from pre-trained network, which makes our job a little bit easier. So let me talk about why that is. Okay. Okay, so to build the first piece of our You Only Look Once network, I mentioned we're going to use a CNN. So what the heck is a CNN? CNN is a convolutional neural network. And the reason it is so helpful for extracting information from our images is because it uses a combination of 2D convolution layers with other nonlinear activation layers and downsampling layers. So essentially, we're able to run something similar to a spatial filter over our images to identify these features and then condense them down ultimately into a classification. Okay. So in the front end of a CNN, right? So you'll see kind of this pattern of these blocks of convolution, ReLU, which is one of those nonlinear activation layers, and pooling layers, which is a downsampling type of layer. And this will be iterated again and again throughout the CNN, depending on how complex it is. But in the front end, closer to the input, you'll see the features that are being extracted, right? If we just take the weights in one of the convolution layers and visualize them, which you can easily do in MATLAB, and you should be doing if you are troubleshooting your network and want more insight. So you'll see that closer to the input, you see features, higher level, low-level features like edges, blobs, areas of color, angles of orientation. And the further and further in you get, the more iterations of these convolution, activation, and pooling blocks, you'll start to see what resembles shapes and ultimately the categories that you're trying to categorize into with your classification network, right? So what we can do is not just utilize this to pull out the features, to use these for feature extraction, but any pre-trained network, right? Any network where someone's already done the hard work of collecting all of this data, labeling it, and training a network, we can exploit by using the beginning pieces and then just stripping off the last few layers and adjusting it for our task, right? And you may be thinking, this might be really annoying to go in and manually fix. Actually, you can do this both graphically and programmatically in MATLAB. Okay, So before we dive into the demo, the first part of the demo, let me just explain a little bit more about labeling, because that's what we're going to address. So I mentioned that labeling data is really, really annoying. This is to the point that people actually outsource it so that, you know, those are you human verifications online when you're making an account. Sometimes you'll find those image labeling tasks where they say, click on the squares where you see a traffic sign, or click on the squares where you see a vehicle. Those are all you labeling data for somebody else, because it's super annoying and it takes up a lot of time. So how can we make that process a lot less painful for us, because we probably don't have a ton of grant money to spend on paying someone else to label data day in and day out, right? Also, it's a giant pain in the butt, and it's pretty much torture for anyone doing it. So in MATLAB, whether you're working with signals or even something as specific as audio or images, videos, or even things specific to the automotive space, we have labelers for all of those domains. So you can go ahead and automate that process and not just have someone click there and manually adjust each and every single label, but you can actually run automation algorithms so that you don't have to sit there and do it all yourself and take up lots and lots of hours of your time. So let me go ahead and open up what I'm talking about in MATLAB. All right, let's dig in there. Got my seminars. Let's look at my deep learning. Okay, so I'm going to open up this project file. If you don't know what a project is in MATLAB, it's actually a really great way to package up a whole bunch of scripts and other associated files with your work and send them over to someone. It helps avoid things like having to add path or gen path and things like that. And it's just a better way to share your work with others. Similarly, you can use Live Editor or Live Scripts to share your work with others as well in a more portable and transparent way. So for those of you who are not familiar with Live Editor, maybe you weren't at some of the earlier seminars today, Live Editor is a really good way of telling the story of your script, essentially, and that's why I'm using it as the demo today to explain our demo. You can include pictures, you can include your script, as well as a combination of rich text, headers, equations, and anything else that will easily allow someone to read your script in a way that they understand what's going on. Okay, so here I've already opened up the project, and what I'm going to do is open up the image labeler for you. Okay, so here is the image labeler. So what I did was open it up programmatically by running this command, right? Go back to that over here. But you can also go over to the Apps tab up here and open any variety of really, really useful apps. So not just the labelers, but many domain and application-specific functionalities are here. For those of you doing image processing or signal processing, there are a lot of really helpful apps in those domains. So I do encourage you to check that out in addition to the ones associated with deep learning. Okay, so here's the labeler. I've brought in some of my data, and you'll notice if you look over here, I'm using an image data store. So if you're not familiar with the image data store, it's a really good way to bring in a large collection of files, in this case, images. There's also data stores for signals, text, and audio, etc. And you can make a custom one too. So this is a good way to manage those large collections of files without trying to dump them all into memory at the same time, especially since in most cases for deep learning, your data is so large that you're not going to be able to fit it all into memory. So data stores are a really helpful tool there. All right, so I'm just going to grab a bunch of these images. So let me just select some of them where I want to label vehicles. Okay, so I can label just by clicking on this button up here called label. And you'll notice I have several options. I can make it a rectangle, a line, or a pixel label, depending on what type of deep learning operation I'm trying to do. In this case, we're doing object detection, but you may have cases where you're doing pixel labeling for things like semantic segmentation. Okay, so here we go. Vehicle. Okay, so worst case scenario, you've got someone sitting here going, click, here's one car, click, here's another car, etc. Right? But that's what we want to avoid exactly. So I'm going to select a subset of images and show you how to automate this. So if you're working with vehicles, people, faces, these already have detector algorithms built into the computer vision toolbox, which you can interface seamlessly with the deep learning toolbox. So here, I can go ahead and hit vehicle detector, hit automate, and MATLAB will go in and apply that detector to each of the images that I've selected to try and find the cars. And of course, it might not be perfect, right? And if you notice, my images are rather low resolution. That may be something we want to think about. Is my image too low resolution for robust labeling and robust learning of my model? Do I want to adjust that? Okay, so in this case, you know, if I don't like the label, I can always go in and adjust it. But now I have a first pass, and if I'm happy with the labels, I can go ahead and hit accept. And I can export them. And I can either export them to the workspace, in MATLAB and work with the deep learning workflow there, or I can export to a different file format to go ahead and bring it to another platform if I need to. So this is very flexible. And you may be wondering, you know, Sharon, I'm not always looking for faces or cars in my images. You might be looking for a specific type of biological signal, chemical signal, something in your data that is unique. Well, as a domain expert, you may already have an algorithm that is very good at least taking a first pass and identifying those areas to label. So you can always import your own algorithm or create one, bring it into the labeler, and go ahead and apply it to all of your images. And in this way, you save a ton of time when you're labeling your deep learning data. Okay, so that's step one of our demo here. So the deck that I pulled up here is very image oriented, but there are a lot of labeling tools that also allow you to do things with signals like automatically detect speech, do speech to text conversion, etc. So there are many, many chances to go ahead and automate these processes and make your life a whole lot easier. All right, so let me go ahead and zoom through these. Already talked about those. Okay, I touched upon data stores, right? They're one way to handle out of memory or very large collections of data. They apply across many different domains and can be customized. Another thing to think about is, am I working with images or signals that are very large and out of memory as well? In which case we want things like big image, or in the case of numerical arrays, tall arrays, to help enable us to work with these huge data sets without sitting there and trying to load them in piece by piece. Let MATLAB do that for you under the hood by using these constructs, so big image, tall arrays, and data stores, and you can focus more on what you're trying to achieve. Okay, so I mentioned when you don't have enough data, right, there may be a need for you to either augment or synthesize more. So there are several ways to deal with not having enough data or not having enough data in a specific class or category. And you can either apply random transformations like rotations, reflections, warping or jittering of different things like hue or contrast. So that would be one way that you can work with images. There are similar and analogous transformations that you can also apply to signals and audio signals that, again, are built in and easily usable in MATLAB, especially on these data sets. So you can use things like augmented image data stores to go ahead and apply these transformations, not manually, but just automatically through the data store itself. Okay. Another thing you may want to think about, especially for signals, is replicating your data to essentially synthesize more of a specific class or category. This comes up a lot for medical images too. You may have a ton of examples of normal, healthy cells in your biopsy images and just a few examples of cancer cells in your images. How do you balance those classes? So in this case, these types of transformations can come in handy. You can also deal with it on the layer level. There are class weighting layers that allow you to also help with these imbalances. There are a ton of examples in the Deep Learning Toolbox where you can find these techniques, pull the code from the example, and try it yourself. All right. On the other side, you can also synthesize your data using deep learning techniques. So getting very meta here. But basically, you can train with what little data you have a deep learning network like a GAN or a VAE, shown here, to generate more of your data from random noise. So again, there are examples of both of those types and other advanced network architectures in our documentation. All right. Before I move on, so let me just ask here, Bo, was there anything else you wanted to address kind of on the data side before we move on to modeling? Might be muted. Okay. If there's nothing, you can...
Nope, nothing yet.
Okay, cool. We'll move on. All right. And again, so if there are any questions, the panelists are handling the majority of them, but if there are any questions that are relevant to the entire audience, do let me know and I will answer those too. All right. So on the modeling side, right? So I talked a lot about the data, but let's talk a little bit about the modeling aspect. How do I go ahead and work with this neural network in a way that's not going to give me a giant headache trying to learn how to build one? Okay, so the great thing about MATLAB is there are so many already built-in algorithms. As you may already have seen from the earlier seminars today, there is just a wide variety of different domain related functionalities that you can seamlessly connect to. And the same is true for the accessibility to pre-trained models. So if you're new to deep learning, the last thing you want to do is try to just build one yourself without any knowledge of what types of architectures work well for what types of applications. So we have a lot of the very popular in literature models available right in MATLAB. And I can show you how easy it is to access that either graphically or programmatically in the demo. Okay, and of course, as I mentioned, we have fantastic documentation examples to go ahead and try any of these processes out yourself. You can pull the code from them, adjust them a little, and even try them on your own data. All right, so I already talked about CNNs and why they're so helpful, and especially why they're helpful with pre-trained networks where I can just adjust the last few layers and go ahead and use even less data than I needed if I was training a new network from scratch and adjust that network for my task. So some of the things that make handling these networks and doing transfer learning easier in MATLAB are apps like the Deep Network Designer and the Experiment Manager. So the Deep Network Designer, as of 20A, I believe, yes, as of 20A, you can do the entire deep network workflow right inside the app. So here, you're seeing how easy it is to either create a new network through drag and drop, right? So I can go ahead, connect those up. I can debug by clicking Analyze. So if there is an error or a warning, I'll know exactly where that is and how to fix it. And I can go ahead, bring in my data, and you'll see here, so let me actually pause right here and show you. You'll see there are augmentation options. So like I said before, if you don't have enough data and you want to apply some random rotations, rescaling, etc., you can even do that right in the app itself. Okay, and then once you've brought that in, you can see, how well your classes are balanced. You want to go ahead and set your training parameters. And these are things that you will be tweaking throughout the process of training your network and evaluating your network. And while you're training, you can view the progress. Okay, and when you're done, you can always generate the code from the app. So for those of you who are new both to MATLAB and deep learning, this is a great tool. Not only are you learning how to do this step by step, you're also learning the associated code and how to do this programmatically and how to automate the process. Now, if you are getting really serious about training a specific neural network for a specific application, you'll find that this point and click thing can get really old if you're trying a very large range of hyperparameters. So for that purpose, the experiment manager can be really helpful. So this lets you try out either different ranges of networks or different ranges of hyperparameters for a given network and look at those results all together in an aggregated sense. And this is a lot more helpful if you're doing things like Bayesian optimization and other tuning of hyperparameters where you don't want to sit there and manually test them one by one. Okay, and this is can be set up in a programmatic way, or it can be set up in an interactive way inside the app. All right. And similarly, all of these apps that you're seeing today have a way of going ahead and exporting your results in a way that's portable. All right, so what does this mean for our piece of the demo, right? So for this object detection network, how am I going to leverage this? Well, I said that what I need in the front end is a feature extraction network. So what I can do is use a pre-trained CNN type network, so a convolutional neural network, to go ahead and do that front piece so that I don't have to build it myself. I can go ahead and use and build upon the work that someone else has already done. Okay, and then the back half will be YOLO V2 specific detection network. So I can use a pre-trained network and load ResNet 50 with a single function call if I've already installed it in Deep Learning Toolbox. But just for demonstration purposes, you can also bring in networks from other frameworks through the ONNX format, so the Open Neural Network Exchange format. So that's what is being shown here. Whoops. There we go. All right. So you have both options. And of course, you can also build your model inside MATLAB and then export that model through the ONNX format as well. All right, so let's go ahead and bring that in. So import ONNX network is a function that will allow you to bring that in. And ResNet 50, in our case, is actually pretty heavy duty for the things that we want to do. So we're going to strip off a bunch of the layers after node 140. And we could do that programmatically. It might take some time to finish, but a lot easier is just to find that node in the Deep Network Designer and erase everything after it graphically. Okay. And now we can go in and fill in the rest of our YOLO V2 network. And that's what's being shown here. So you can actually see all the parameters for a given layer on the right. When you're doing this programmatically, which is also a perfectly valid way to do it, you would be typing in those parameters one by one. And if you're working in Live Editor, MATLAB will guide you through the process of the next input of the function. So it's really not that bad. But if you prefer to be able to see all the parameters at once, this is also a really nice way to handle your networks. All right, so I've connected the first and the second piece of my networks all together, like so. And of course, you always want to debug and check. All right, so no errors. And then I know it's safe to proceed to the training step, okay? Oops. All right, so back to kind of our discussion of CNNs. Another really important thing about CNNs is that you can visualize through the weights and the biases what parts of our image are actually being focused on. And this is not only just fun or makes for trippy images, but also really allows us to go in and troubleshoot what is happening inside our network. So we don't treat our deep learning network like a black box. We want to glean insight from it and be able to tell what went wrong. And this doesn't just apply to images. If you're working with signals and using a network like an LSTM, a long short-term memory network, you still want to look at those weights. Looking at the weights in the case of a time series will allow you to see if there's a time dependency, if you're working with a network like LSTMs, between the different time points of your signal. So whichever way you are using your network, you do want to look at how it's processing your data through various visualization methods. Okay. So I'm going to kind of gloss through this because we're running a little short on time. But actually, so I'm going to show you the image portion of this, and then I'm going to pivot over to some of the signal-specific stuff soon. Okay, so in terms of the image domain, there are a lot of different operations that you can achieve through deep learning. There's object classification or recognition, detection, and semantic segmentation, which we briefly mentioned could help in cases where you need a more granular classification on the pixel by pixel level in the image. So here on the bottom right, here's an example of free road and vehicles being labeled at the pixel level. And then here's an example of brain tumor segmentation. This is actually a documentation example if you want to check that out. And this is on 3D data as well. So a very flexible workflow. And here on the lower left, you're seeing an example of artificial upscaling of resolution of your image. And this is just one example of image-to-image regression. There are many other image processing techniques that you can apply to your images using deep learning. All right. So, okay. So I'm just gonna pause the screen here so that I can pull up my more general slide deck. So please bear with me as I do that real quick. Here we go. Deep learning. Let's see. To deep seminar. Pardon me, you guys. Looking through my very convoluted folder structure here. Deep. Okay. Oh, where are you, buddy? Here we go. Here we go. All right. All right. Found it, you guys. Let me just get to the correct slide here, and then we shall continue. Okie dokes. All right, I'm gonna unpause. All right, so we've looked at the apps together. Now let's also talk about the hardware side of the modeling piece. Okay, so for hardware acceleration, I've said already that any kind of parallel computing that you can get your hands on, so whether it be an external NVIDIA GPU that you plug right into your computer, or a high processing computing cluster that you have on campus and you have access to, or cloud resources. So those are all things that if you have, you want to go ahead and use. And because MATLAB has all of these built-in functionalities, if you go ahead and install Parallel Computing Toolbox, you can make use of any of these resources in a built-in way, right? So you don't have to sit there and try to manually code in CUDA to use your GPU. You can just use that flag in MATLAB in your hyperparameter options, and you're good to go. And your training doesn't have to feel like watching paint dry. Okay, and like I said before, you can very easily pull models in and out of different frameworks. And this is really important if you're working with the latest research. And you can do that, like I said before, with the ONNX format. Or if you're working with Keras and Caffe, you can import those directly into MATLAB. Okay, so the last piece of my demo that I was going to show you, but I may have to breeze through a little quickly because we're short on time, is just, you know, when I am applying this trained neural network, how do I go ahead and, you know, take a look and visually inspect the images and the results that I am getting and understand if it's working well or not. So of course we can do visual inspection like this, right? These images have been labeled with my trained neural network, with my data that I labeled and the neural network that I built. And these numbers that you see on the bounding boxes are confidence scores. So for instance, in this image, my network is 92% confident that it's found a car right here, right? So you can use confidence scores, and overall you can use accuracy as well. And there are a lot of different metrics of accuracy across different forms of classification. And also in regression, you can also look at root mean squared error to evaluate whether or not your network has done a good job. Okay, and same goes for validation, which is essentially testing that you can do while you're training your network as well to make sure it's not overfitting. Okay, if you are going ahead and integrating your algorithm into a larger, more complete system, maybe it has to be tested for certain standards, MATLAB has good support for that as well. So keep that in mind if you're entering a competition and maybe you're building a system that goes into an autonomous car. You need to make sure it's safe. So if that's something that you have a concern for your particular project, reach out to us so that we can help you know what resources are available. Okay. And then, of course, deployment is really important, right? If we need to get our code onto a piece of hardware, usually we brute force that by turning it into C code or turning into some other code that's compatible for our hardware. In the case of GPU, you would want CUDA, and you may also want to access hardware like FPGA, ASICs, etc. Right, so where MATLAB comes in handy, especially if you're prototyping and you don't want to keep hand coding for tiny changes, is the ability to generate C code or generate CUDA code, etc., directly from your MATLAB algorithms. And in the case of neural networks, you will actually get code that is specifically optimized for neural networks with the Intel, ARM, and NVIDIA libraries. So not only are you making use of a lot of, more than 15 years of work in the coder areas on our development side, you're also getting better performance out of those optimized libraries on the Intel, ARM, and NVIDIA side. So if performance is extremely important to you, or you're doing a real-time detection or some other type of algorithm, this may be of interest. Okay, and if you're scaling up perhaps to a web interface or mobile interface, and you expect maybe tens of thousands, hundreds of thousands to click at the same time, and you want them to get the result back in a timely manner, you may want to think about other ways of support like MATLAB Production Server that can reduce that latency and allow you to scale your algorithm up without having to recode everything for the environments that you're deploying to. Okay, so I'm a little short on time, so let me just kind of describe this step to you without going through the whole thing. It does take some time to generate the code. Basically, when you run MATLAB Coder for C or GPU Coder for CUDA, you go ahead and take your MATLAB algorithm. So this is the original MATLAB algorithm, and then you create the C or the CUDA code from it through MATLAB Coder or GPU Coder. And at the end of it, right, here is the report of the produced code. You're actually able to trace exactly which parts of your MATLAB code match up to the C or the CUDA code. And you can go in, you can customize the end result as much as you need to, and this becomes extremely portable compiled code that you can run on hardware that you can use to test your code.
As deep learning on RAMP, it teaches you the very broad aspect of deep learning, from importing the data through building a model through the drag and drop interface. Such courses are also available in other topics such as machine learning and MATLAB. We also have more focused courses. So if you're interested in accessing more advanced or going deeper into some topics, you will have access to this if your university have the campus-wide license suite available. And so we also know that some of the faculty members actually assign these materials in the courses as homework and use class time to discuss some of the domain-specific examples. We also have this data science 4-course specialization on massive open online course platforms such as Coursera. So this is a 4-course specialization that talks about feature engineering, data analysis, visualization, and etc. So you can freely audit the course. Alternatively, you can also get a license from the course and then put it onto your resume or further build your portfolio. One thing that is happening particularly now is that we're currently having Advanced Alzheimer's Research Data Science Challenge by us partnering with Driven Data Competition. So this is a good example, a good opportunity to practice some of the data science skills. You will get the tools needed throughout the duration of this competition, as well as technical assistance. And we also will provide the MATLAB benchmark code for you to learn and also compare with the code you have developed. Not to mention that the price is pretty worthy here. And you have access to other materials. So in the chat, there were people asking about the materials. So we'll send out the slide deck after today's event. There's deep learning on RAMP. We also have tutorials, examples in the form of live script Sharon has just showed. We also have deep learning training and a lot of white papers to help you get started. And so MATLAB is also a leader in the field of data science and machine learning, as classified by the global independent research analyst firm Gartner. So we have tools in many specialized domains, such as signal processing, deep learning, machine learning, so you can quickly leverage these vertical capabilities in the unified platform here provided in the MATLAB. Quickly carry your code from prototyping, development, or further goes back to the data labeling, data ingestion, all the way to code generation to a productization platform. Let it be a GPU, let it be a ARM or FPGA or other architectures. And last but not the least, very important, so here we have an awesome MathWorks customer success team so that we can help you with support your projects, studies, or initiatives. We can also help build or integrate your curriculum, these kind of topics into your curriculum. If you have any questions, you can also send email to this address. You can also address them in the Q&A or chat, or also fill in the post-event survey. So the post-event survey is going to pop up after you quit the WebEx. But before we let you go, we have a poll. So iJump, could you pull up the poll? So we are
Okay.
interested to let you know what kind of topics you want to explore further after the session today. So I noticed in some of the Q&A questions, some people are very interested to explore more on very specific techniques. Say, how do I apply deep learning to my signals, or to my images, or to my audio data? Some people are very interested to see what specifically do we mean by code generation into a productization platform. So we have a pool currently shows up, and we would want to understand better on what other similar topics you would be interested in. So it can be what's new, or how do you speed up your code. It can be deep learning, or specifically for image processing or computer vision or signal processing. It can also